Next speaker is Leticia Cugliandolo from LPTHE, and she'll tell us about active phase segregation, 2 dimensions.
Okay, so thank you very much. So first of all, I want to congratulate Deepak for this very nice prize. I want to tell you that I met Deepak in Istanbul in a school in '93, I think it was. I was a young postdoc at Rome at the time. I didn't know a lot about statistical physics because my PhD was on something else, high energy. But okay, I enjoyed the lectures that Deepak gave there. It was a wonderful school. And in particular, apart from Deepak being there, Beppe Gonella was also a student coming from Oxford at the time. And okay, so well, we enjoyed all these statistical physics lectures and so on. And much later, I met Beppe again, and we started a collaboration on active matter. And I'm going to tell you about part of what we have done over the last 4 years, more or less. So the rest of the people who are here are mostly associated to him. So they are former PhD students from Bari who moved around. And the ones here, Damien Levis was my former PhD student from Paris, working on frustrated magnetism, but then he went into active matter, and Ignacio, that probably you know. Okay, so let me make a short summary of what I'm going to tell you about, and then, well, depending on time, I will cover all these topics or less than the ones we actually listed here. So the first thing that we wanted to do was to characterize completely the phase diagram of active Brownian particles in interaction on 2D. So 2 dimensions will play a special role here. And in particular, we were interested in the issues about melting, which are not even so clear in the passive limit. So we wanted to also consider the passive limit of this problem, then add activity and see how activity modified the different phase transitions from solid to exotic to liquid, as you will see. And then there is this other special feature of these systems, which is called motility-induced phase separation, which is a special phase which appears at high levels of activity. And most of my talk will focus on what happens when you enter this phase, like doing a quench, like coming from a disordered initial condition with given parameters, and then seeing how this phase separation occurs in the course of time, and which are the features that we can identify of the dynamics of the system in this special region of the phase phase diagram, sorry. So first of all, I just recall the definition of the model. It was already given in different talks, but what is different in my case is that I'm going to consider many of these particles in interaction, and the potential of interactions between them is going to be purely repulsive, very short range, quite hardcore. And although I have inertia here, I will consider parameters, mass and friction coefficient, which are such that we are almost in the complete overdamped limit, although in the numerics, this term is present. And then there is this other feature of this problem, which is that, well, the disks in 2D have a special direction along which there is a force acting, but this direction performs a random motion, random rotation controlled by this equation over here. So this is the angle that the force has with a certain axis, horizontal, say, and this is a white noise. And again, okay, there is the force acting here, there is thermal translational noise, which is white, and there is the interaction between the different particles. So this problem has basically 2 control parameters that we will use. One is the Peclet number, which is an adimensional number that measures how much activity there is compared to thermal energy. So this is the work performed by the active force here, and this is thermal energy of the bath. And then there is the packing fraction, or the global density, if you wish, occupied by the particles on the box in which you put them. Okay, so just to recall, in the 0 Peclet limit, these particles just are passive. They do some kind of random motion. They are, of course, influenced the motion by the presence of the other particles, which are in repulsive interaction with the one I highlighted. But in the active case, when you apply the active force, there are these persistent motion appears with long periods over which the particle goes more or less straight and then turns round and so on and so forth. And the active force is correlated in time exponentially, as it was just mentioned in the previous talk. So now let me summarize what is the phase diagram of this problem that we obtained in this paper here. And we call it full phase diagram of active Brownian particles because we wanted to span, the variation of parameters packing fraction and Peclet over, whole range of variation, and not just focus on either high Peclet or low densities as it was done in the past. So here is the equilibrium limit. Okay, this is a logarithmic scale, so you can imagine that the equilibrium limit goes to the left, but imagine that it's here. And then what you see is that there is transition in a series of steps, as you expect in a problem in 2 dimensions. So there is first, if you wish, a very high density, a solid phase. There, okay, you don't see it, but there's a little bit of violet, which is the exotic phase that I will characterize in a second. And then there is coexistence between which phases? Well, exotic and liquid. So what we observed, and this is following papers by Werner Kraut in École Normale, where he studied the passive case before us for hard disks in particular, is that this two-step transition from solid to liquid in these kind of systems goes on through the second transition, the one between the exotic and the liquid, being of first order and not Kosterlitz-Thouless kind, while the one between the solid and the exotic is Kosterlitz-Thouless like as expected. Now, if you switch on activity, what you see is that this region of coexistence dies at a certain point here at around 5 Peclet for our parameters, and then disappears. And then the transition between the exotic and the liquid continues to be of Kosterlitz-Thouless kind. So this is what we see from measurements of different kind of correlators, distributions of local densities, distributions of local exotic order parameter, and also from the identification of defects and their unbinding, their densities, and other features of those topological defects. Now, if you go towards higher Peclet, this new phase, which is here depicted in gray, which we call, it's called MIPS, or motility-induced phase separation. What the system is doing there is that it's separating into dense and dilute regions in the space, in the normal, well, there are dense parts and there are dilute parts. And this is a kind of phase separation mechanism which is driven by this activity, because recall that the interaction between the particles is repulsive. So they don't want to get together in principle because of the potential of interaction to body one. But because of the presence of the activity, they can perform this kind of phase separation phenomenon. Other things could be said about what happens with the defects, geometrical phase transitions, a little bit like what Deepak was discussing this morning, but I won't do it in this talk. Okay, now there is this motility-induced phase separation phase here, and I will go back to it later on. So this is just to recall what I said with words, the fact that because of the activity on the boundaries of this dense part of the system, where the system is very compact, the particles are very compact, you have particles that because of the activity they try to get in, they just are, colliding on this bubble here, on this droplet, let's say, here, and they just keep on colliding there. On the opposite direction is the opposite, and this is roughly what is keeping this dense droplet together. Okay, so now one can ask the question, what is the structure? What is the internal structure of this dense part? Is it just homogeneous, completely nice? Is it fractal? Is it not fractal? Are there holes in it? So there's many things which can be said. I want to tell you some of them. So the different colors here represent different orientational order, different exotic ordering of the particles within the dense region. So you can imagine that these particles are more or less perfectly oriented, perfectly organized in such a way that each of them has 6 neighbors around, as is the perfect crystal in 2 dimensions with no fluctuations. But the orientation of this perfect crystal is different where I am painting the regions with different colors. Okay, this can be made quantitative. I'm just saying it with words. But something else that appears is that there are gas bubbles within, and these gas bubbles appear and disappear very dynamically and very quickly, and some of them are expelled out of the dense, some other ones form. And these bubbles appear in the interfaces between these different exotic order phase. And along these interfaces, they are like, these are like lines, curves actually, of defected particles, in the sense that one has 5, the other one 7, 5, 7 neighbors, instead of having the 6 preferred in 2 dimensions. I will tell you this in a second. Okay. Yeah, I will tell you. Yeah. Okay, so one can now we'll try to compute something and be a little bit more quantitative. So for example, here, what I'm showing you is how the typical radius, typical size, I wouldn't call it radius, linear size of this dense region grows in time. And there are different regimes. There, here, you enter something that is called the scaling regime. And there you see that this growing length goes roughly like t to the 1/3, independently of Peclet. So these are different Peclet values. And that this exponent seems to be the exponent that you expect in an Oswald ripening kind of mechanism of phase separation. But then you can ask, is it the only thing that is going on or not? And if I have time, I will discuss that. How do you extract this growing length? Well, from the analysis of structural factors, for example. But then, okay, I come to your question. So how do I identify, the fact that there is different exotic orders and the interfaces? For example, I can look at the distribution of the local exotic order parameter under a modulus. This is defined here. It's something that allows you to identify the different orientational orderings. And what one sees is that while the typical length of the dense part of the system grows, as I showed you before, grows, but eventually saturates to some value that grows with the system size, that is proportional to the system size. So there is a macroscopic separation into dense and dilute parts in the system. The exotic length that I can more or less visually see here from the size of these color patches, it does saturate, but it saturates to a value which is finite. So what we are seeing is that, okay, you will have this macroscopic dense part, but it's a patchwork of finite size regions with different orientational order. Yes, it is. Yes. Yeah. In the passive limit, you wouldn't see that. Yeah, you would heal this. But of course, the dynamics is so slow that then you have to be careful. But if I come to the formation of this dense phase, the way in which it happens is more or less by single particle attachment. And then you can organize better the orientational order within the dense phase. While here there is also cluster-cluster aggregation. And when two clusters with different orientation attach together, it's very difficult to reorder a whole thing. So
nearest neighbor patches, the orientations would be uncorrelated?
Yeah, I would say so. Yes,
Okay.
Yes, because the correlation function decays exponentially and rather quickly. So yeah. Okay. So I can, make these claims a little bit quantitative by showing you pictures. So this is how this length of the size of the dense part scales with L, the system size, and this is for different system sizes. This is linear size, and this is the total number of particles that we have here. And you see that for very large system sizes, there is collapse here, and the saturation is towards a value that depends on the form of the global system that we chose, and in the way we chose it. Okay, it takes some certain value that we can calculate as well. While the exotic length, it tends to saturate here to some value which is finite. You see, this is not scaled by L, and there is a very, very, very slow growth of this ordering that goes with an exponent which is much smaller than the 1/3. It's like 1/3 of 1/3. Okay, so this is for what's going on, and then there are the bubbles, and then one can also study how the length of these bubbles grows in time, and compare it to the growth of the exotic ordering, and it's roughly of the same order. It's very slow as well, and this also saturates to some finite value, and you can look at the distribution of the sizes of those bubbles, and it's a power law with some cutoff that depends on Peclet. And okay, we can say more about this exponent, but it's not very interesting here. So now let me spend the last 20 minutes to talk about something more recent that we have done. So it's how the dense component actually grows in time. What are the mechanisms behind that, and whether we can understand it a little bit better than done so far. So I'll go back to this plot that I have already shown you. So this is the growth of the dense component, but then we can also look at the number of clusters, because at the beginning it's not that there is just one cluster and all happens with one cluster. At the beginning, what happens around here, let's say, is that there's nucleation of very tiny regions where particles aggregate, and then they grow a little bit more, and then they enter this scaling regime. But still in the scaling regime, there are a lot of clusters. And as time goes on, there are still many, many clusters. And you can count, the number of clusters and see that the number of clusters is case in time with some power law that is related to the way in which this length grows in time. So a lot has been done about the average, I would call it this way, scaling regime. So this is an average over everything that is going on in my system. But now we want to go beyond. So we want to have a look at each of the clusters and try to follow their dynamics and try to see whether there's only also a ripening of single particle attachment or there is something else going on. So the goal is to better understand the mechanisms for the growth process and in particular try to see if they are like the ones of the passive case or not. Passive now, I need to put some attractive potential between the particles because otherwise they wouldn't aggregate, right? So what I want to do is compare the dynamics of my active, purely repulsive system with a similar system of passive particles, but which have some attraction. So these are just snapshots of instantaneous configurations at times for each of the two systems, which are very different, but for which the global length of the dense part is roughly the same. So you see that for the passive case, you can see that, okay, you have also clusters. Their surfaces, their interfaces are not very rough. If you zoom out here, you see, and this is the answer to your question, Yarid, that the clusters, each of them has a single color, so a single exotic ordering. While in the case of the active case, you see that here, for example, you have a big cluster with different colors on it. The interfaces are much rougher, and okay, there are these internal interfaces between different orientational ordering. So, well, we have visual facts that tell us a little bit about how these systems are organizing. And something else that I didn't tell you is what is the color code that I was using for the clusters here. So there were blue and there were gray. So the blue are from analysis that we do later on, quantitative analysis. They are regular in the sense that they are compact, while the elongated ones that you can see here and even more here, they're fractal in the sense that the relation between their surface, their area and their radius is not controlled by a power 2. So we see rougher interfaces in the active, we see homogeneous in the passive and heterogeneous in the active orientational order within the clusters. And in both cases, we see regular in the sense of non-fractal, dark blue clusters and large elongated gray clusters. Then you can look at, well, distribution of cluster sizes, because this is a typical thing that is done experimentally. And you can compare, for example, with the experiments done in Lyon. And what one can see, if one looks a little bit carefully about the numbers, is that, well, the clusters here are much smaller than the ones that we can reach with the numerical simulations. This system is more dilute than ours. So the clusters are small and far away, while we have a lot of clusters all touching almost each other and moving a lot, as you will see. So I could be more quantitative on the analysis of these distributions, but I prefer to not do it now. So, okay, we go to this. This is just the average mass over all the clusters as a function of time for different Peltier numbers. And there we see, well, this growth that goes like t to the 2 over 3. That looks like being just dimension over 3 compared to the one of the radius that I gave you before, that the linear length that I gave you before. These curves scale very nicely if one, for example, uses the time of entering the scaling regime and the mass of entering the scaling regimes that depend on Peltier in a way that we can identify. So everything is quite clear at the level of the averages. But now you can say, well, okay, is the dynamics going on in the same way as for the, let's see if I can put the videos, as in the active and in the passive. So this is a video for the active case. And well, I don't know if you can see it. Maybe there is a zoom that will appear. Yeah, there is a zoom. If you pay attention, there will be attachment of different clusters, and they even change color when they attach, because if you attach two round, nicely clusters, well, typically they will become elongated and maybe they will become fractal. So there's lots of things going on, like a change in nature, a lot of fractality, and so on and so forth. But a lot of cluster attachments. Well, if you go to the passive, you will see that the clusters don't move so much. There is also changes in color because of the way in which we define the fractality of these problems. But okay, if you pay attention, there will be less cluster attachment, much more growth driven by just the, I'm left, what does it mean? Oh yeah, okay, by the normal Oswald ripening. So in both cases, there is Oswald ripening. But in the active one, there is more displacement of the clusters, much more, finding each other and getting together. They also break more, and they can recombine, so they can expel a piece, come back, and so on and so forth. So these comments here pinpoint that something more, something also like diffusion limited cluster-cluster aggregation may be at work in the active case, more than in passive one. So now what we try to do to understand a little bit better the motion of these clusters is that, for example, we extracted one cluster from the bulk, we put it in under conditions which were the ones of the bulk, in the sense of surrounding it with a gas with the same conditions as the one it had when it was in the bulk, but now it's isolated. And then we let it evolve in time and we see what happens with its evolution. Just to tell you that there is this break-in and this strange motion and so on and so forth. So this is what happens with the comparison between, the active on the left on that side and the passive on this side here. And you see in the passive, nothing is going on, basically. While in the active, there is a lot going on. It changes a lot its form. It breaks a piece here. It will capture another one. And it displaces a bit much more because this red trajectory here is the motion of the center of mass of the two clusters. So you see that here it moved far away. Here it's always there. I mean, it's not doing much. Yes. Okay, so we chose the parameters so that the density is the same, the global packing fraction is the same, and we chose times. So in the global case, no, when they are in the bulk, I was showing you different times, very different times, but such that the R of t was the same. So in the passive, since everything is so slow, I have to go to much longer times than in the active. But the R of t, the global one, was the same in the two cases. So that was the choice of comparison that we made. Yeah. Okay, so so now we can go and look at the clusters one by one and look at their. Sorry, say it again.
Sorry. Is the growth law the same?
The global growth law is the same. It's the t to the 1/3 in both cases, but my message will be that you can get t to the 1/3 in different ways with different mechanisms. And just to see t to the 1/3 is not enough to say that you only have Oswald ripening. So that will be the message of the talk. So this nice picture here, what is it? So what we have done here is that we have looked at in the bulk, in the global system, each of the clusters, they have a mass. So we have, ordered here the masses of all these clusters divided by some number. Okay, this is just to normalize. So we just order them like that and look at them in the course of time. And this is just to illustrate the fact that we have an algorithm that allows us to follow the clusters in time, which is not obvious. So it's a tracking algorithm that gives an identity to each of the clusters. And up to a certain time, we can keep this identity. I mean, we can realize, that this cluster is doing this other one is doing some other thing. Of course, this cannot go on forever because the clusters merge, they break. There are a lot of issues about this. But for a given amount of time, we can be certain that we are identifying correctly our clusters. And when these things, well, okay, we can discuss what these lines mean, but it's just an illustrative thing, which I thought it was a nice picture. So we go back to this law and try to understand the cluster origin of it. So the tracking of individual cluster motion, as I said, we can do it. And what kind of quantities we can look at? For example, we can look at the total active force that acts on each of the clusters. And for example, we can correlate it in time. So we can, for each cluster, we have the force at time t prime at time t, and the average is over the clusters here, and or over the different runs over the clusters. And then what you see is that it decays exponentially in time as the individual active force on each of the particles does. There is a prefactor here, which is different. It depends on the mass of the cluster. So for example, here, if I distinguish my clusters by their mass, and I average over the ones which have, within some window of masses, then I can, compute this same average here. And what I get is that this F squared depends on M. This is the mass of the single particle, and this is the force acting on a single particle. And the decay time of the correlation of the forces is the same as for the single particle, actually. We can also look at the local torque, the torque on each of the clusters, and see that it's very low for these active Brownian particles. It's irrelevant. And for this reason, there is no rotation. These clusters don't really rotate. But then these forces are acting on the diffusive properties of the clusters. And in the way they do is that in the diffusive regime, the diffusion constant will depend on Peclet, but it will also depend on the mass of the cluster. So each cluster will diffuse in a different way, depending on its mass. And the way in which this diffusive constant depends on the mass is through a power law, and a power law which we measure it's a half. Well, around, it's numerical, right? It's close to a half. And the growth with Peclet goes like a Peclet squared as usual. So how do we conclude that? Well, we looked at, as I said,
this total active force is the sum of the forces on each particle
in a cluster.
In a cluster.
In a cluster. So if I select clusters of a given mass around a window, of course, then this prefactor here depends on the mass I'm looking at.
Okay, and that's like some of the individual active forces acting on individual particles.
Exactly. So I sum over all of them.
So then it will have some central limit theorem, or like for the distribution of F?
It would be n to the -1. If they were independent forces acting on each of the particles, then you would get a m to the -1, but you get n to the -1/2.
Okay.
Yeah. So I'll give you two possible reasons for that, for this change from -1 to -1/2.
So Leticia,
yes.
These, in 2D, the Stokes-Einstein would give you the value that you have, right?
I know. Yes. Yeah, I know. But since I don't know this is the origin of it, I don't say it. Yes, but I agree. Yeah. So now I have, this is the full displacement of the clusters. So the position is of the center of mass of each of the clusters. I look at it, how it moves in the course of time. I compute the square of the this difference, and then I sum over all the clusters. This number depends on time because it decreases in time. So it has to be a little bit careful about that, but we can handle it. So when you do this, we obtain that, okay, it goes to diffusive regime, and then the diffusive constant, this is of all the clusters, right? It goes with Peclet as Peclet squared. So this is one of the things I showed you before, and you can see it here. It's diffusive, it's increasing with Peclet, and okay, if you look at the dependence with Peclet, you get this Peclet squared. Now I look at it cluster by cluster, and I look at the mean square displacement of the center of mass of the clusters within a window. So I have a distribution of these diffusive constants that depend on the mass. So, okay, I can do it carefully. Doesn't matter so much how we did it, but the point is that this diffusion constant as a function of the mass decreases as m to the -1/2. And these are different Peclets, and okay, they are increasing with Peclet moving upwards because of this Peclet squared. But here, the best description of these data points, which are very noisy, but okay, this is what it is, still certainly not -1, is -1/2. Now, as I said, sum of random forces would give m to the -1. Possible reasons for that. There is a recent paper by Alex Solon and a collaborator where he looks at the motion of a passive tracer in a dilute active bath, and he also derives an m to the -1/2 here. Of course, he was focusing on a passive tracer. We have the clusters, but possibly there is a mechanism of the same kind which is going on here. Now, what happens with passive systems? I mean, if I look the same, if I do the same analysis for the clusters in the passive system, I get n to the minus 1. So what this means is that the active clusters are diffusing more not only because of the Peclet squared increase with Peclet, but also because they decrease, D decreases slower with them. There's a half compared to 1. And this, for example, is the kind of, well, the mass is changing a little bit in time, but each of the clusters is losing, gain in mass. So you get traces like this, for example, for different active clusters, while for passive clusters, nothing happens, basically. Passive clusters remain the same. Okay, another argument that one can give has to do with the organization of the active particles on the boundaries of the clusters, but I will jump over this. Surface effects are very important, and because more or less all the active particles on the boundary are oriented, right? Because they are keeping together the cluster here, also here, but okay, this is just some analysis of how the velocities of the particles are arranged, and the forces are arranged. It's another possible reason why we get this difference with the passive ones. Yeah, something I forgot to say from the previous one is that if we analyze the motion of the isolated cluster from the bulk, and we go to really very, very large masses, then we see that this there is a crossover basically from the m to the minus a half to m to the minus 1. So both, if I use Alexis Solon argument, it's as if the effect of the bath is losing importance when the clusters are sufficiently large. And if I use ours here, well, the surface effects are less important if your cluster is very big. So both of them tend to say that for very large clusters, one has to recover this m to the minus 1 of the independent orientation of the forces. But in the bulk, we cannot reach this limit. We don't see it. While for the isolated clusters, we do. Okay, so last thing to say is something about diffractality. So now we can analyze all the clusters one by one and do, for example, these plots of their mass against the size, linear size, and see whether they follow size to the squared or they deviate from that. And what you see is that they do deviate from that. They pick up some fractal power 1.45, it turns out to be. And these scatter plots are scaled in such a way that in vertical and horizontal direction, I'm dividing the mass of the individual clusters and the size of the individual cluster by the average over all the clusters. And you see that it's, well, it's around 1 that the breaking point occurs, that the crossover occurs. So the clusters which are smaller than the average are regular. The clusters which are larger than the average are fractal. Okay. This actually also occurs in passive cases, and here there are 2 examples. It occurs in diffusion limited cluster-cluster aggregation, indeed. And this is an old paper where you have this same power. For the same kind of comparison. And this is a more recent paper by Das and collaborators, where he also finds this power for passive Lennard-Jones systems with attractive interactions. Now, last thing I want to say before the end is that, okay, I'm claiming that there is cluster-cluster aggregation, but can I get the 1/3 from it? So can I get the dynamic exponent z equals 3 from an argument like this, and instead of an argument like Oswald ripening? So using this growth of the typical length with a z, and using that the diffusion coefficient decreases with the mass with some exponent alpha, it could be done, with the simplest possible argument of cluster-cluster aggregation, obtained a relation for the z with the fractal dimension of the clusters, the alpha, which is here, the dimension of space, and the dimension of the trajectory that the clusters are following. So our clusters are diffusing. So actually this term cancels out because 2 minus 2 is 0. So the only thing that remains is this. So now what happens? If I look at the regular clusters, the ones which are smaller than the average, df is equal to d is equal to dw is equal to 2. So all the d's are the same. Alpha is a half. So if I plug it in this expression, I get 3. So I get the same exponent as for Oswald ripening, but with a different argument. Now, if I look at the fractal ones, df is different. D and dw are the same. Alpha in the bulk, I still see a half. So in principle, I should put a half here. So then I get that z, which is a bit smaller than 3. So with this argument, regular and fractal clusters are behaving differently, and they are getting different dynamic exponents. Now, if I look at how the growth goes with time, and I now distinguish, the growth of the fractal, the minute I finish, and the growth of the regular, well, I see that indeed the fractal, which are here, are getting a z which is a little bit smaller numerically. So the power here is a bit larger than the 1/3, and here is well, more or less parallel to that. Now, how could we say that the average gives me 3 if I have different values here and there? Well, the thing is that I have many more regular clusters than fractal clusters, actually. If I count the numbers, these are more numerous. This is logarithmic scale, so I have like a factor of 4 or 5. So, it's as if everything is controlled by the regular ones when the average is considered for the z, and these are the ones which are, getting the final result. And this actually I made a mistake here, because if you look at, well, it's slightly larger than 3, but not that much when we do the Okay, now last thing to say, although we don't measure alpha equals 1 in the bulk, but if I insisted in writing alpha equals 1 here, well, I would get 3 as well. So this remains as a, not very well understood. I mean, numerically, we don't see this alpha equals 1 in the bulk, but when we extract the clusters, we see that the very large ones should go with the alpha equals 1. So I recover again after. Okay, summary of what I did is very quickly, I told you about the phase diagram. I didn't tell you much about the defects, but we have a full analysis of the effects in these problems and along the phase transitions and so on. The importance of the exotic and the bubbles, and then all this story about the growth of the dense component seen from the cluster motion. Thank you very much.
So how does the clusters, typical clusters look for system size? Like, if you...
Compared to the system size, you mean?
Yes. So if you take a double system size, if you double it, so you have more clusters of the same size, or if you have a larger cluster?
No, I have a distribution of cluster sizes. So I didn't say it much because
No, but the distribution is exponential.
No, because I showed you the exponential decay. I didn't show you the curves completely. I said that I could say more about them, but I didn't say it. So the distribution that I had somewhere here. So actually here I cut the axis. There's a lot of things going on afterwards.
No, but I'm just saying that what is the answer to these questions? Like if you take a system, if you double the system size,
yes,
do you have more clusters of the same size, or you do have a large size clusters?
Well, it depends how much time I give to the system, no?
No, in stationarity.
I'm not in a stationarity. I'm in the regime in which the clusters are growing. So I'm in a scaling regime.
So
but
just my doubt is
not
that
stationary.
My doubt is that if it is exponential distribution, how can it support a large cluster? Because
still, when I'm showing these curves here, this curve is when I enter in the scaling regime. This is a little bit after. This is a little bit after. It's still very far from saturation. So all these clusters are growing, and I'm still very far from just getting one single cluster with a.
But if it is an intermediate step, it will be in the cosenic regime also. If it is exponential distributions, I don't see how.
It's not an exponential distribution. I cut the distribution here. You
but
see,
is it a power law?
It's more complicated. There are two regimes of masses. So for very small clusters, it's exponential. And for short times, sorry, for very short times, it's exponential, and it's what these people measure.
But what you
But then I have here the approach to a plateau in this scale, and then there will be another regime here that I'm not showing you in this picture, but I can show it to you later. So the distribution is very complex.
But the general, okay, sorry, I think.
Yeah, I can show it to you later. Yeah.
How does the lifetimes of these clusters look like, especially like small clusters versus the very large ones?
How is
the lifetimes? Like how long they survive for before like dissipating?
Well, it depends on the size of the cluster, of course, and we can have a look at it. But for example, in the analysis of the cluster motion that I did, the diffusion can give you the analysis of the diffusion of the clusters that I showed you. Where is it? So for example, here you see at least for 1,000 time steps with respect to time to enter the scaling regime, which is okay, also 300 more or less. So 4 scales, let's say 10 to the 4 times that time to enter the scaling regime, my clusters survive and I can follow them, you know, more or less one by one. I lose some, but I can follow a consistent amount of them. So they survive at least that time scale.
Is there like a problem of them not like surviving long enough to have like these supermassive clusters?
No, at
It's
the
not-
end, they, well, in the bulk, you mean?
But yeah, you know, because you said you found numerically just, you never found alpha equals 1.
No.
And like my thought was maybe just, do they survive long enough to get supermassive clusters that just
No,
scale up
I'm
and-
getting
don't-
more and more massive clusters.
Okay.
Yeah, I'm still getting more and more massive clusters in the bulk, but you know, for some reason, I don't get into the regime of this m to the -1 when I am in the bulk. I don't know exactly why, but okay, this is what it is.
Yeah, it's okay. I was turning it on. Yeah. So, you know, in terms of the distinction between Ostwald ripening and cluster-cluster aggregation, I guess the cluster-cluster aggregation is also a mechanism by which in sort of normal system, in a passive system, you form the dense phase
Yes.
from a supersaturated gas, let's say.
Yep.
And the same substance at warmer temperatures might well undergo the phase transformation through Ostwald ripening. So qualitatively, what's sort of the distinction that I should be thinking about? But let me also just add one thing that seemed to be the answer to my
Yes.
own question is, but I want you to elaborate on it, is, I mean, Ostwald ripening you think of as occurring through the accumulation of either monomeric or small cluster
Exactly.
increments, right? So here clearly that was not the case.
There's still that. There's also that. There's both. In this, when I look at the active problem and I look at videos and I see what is going on, there is Ostwald ripening, but there's also cluster-cluster aggregation. So I think that both mechanisms are there at work, and it happens to be that they both give you z = 3, basically. So, you know, it's a combination of the two of them in the active case.
Did I understand correctly that the fractal dimension of these clusters was, well, it was 1.5 roughly,
Yeah, roughly.
0.45?
Yeah, yeah.
So the Stokes-Einstein argument that I gave doesn't apply because it's, I mean, there it should go as the 1 over the radius.
I know.
So if it's compact and it's 2D, then you'll get that.
But for the regular, it works. So this is
The
why I
regular, it
say
works.
that,
Yeah,
you know,
exactly.
I don't want to use it because it doesn't work for the fractal, but for the regular, it works.
Yeah, exactly.
Actually, I wrote it in the paper and Beppe told me, you know, erase it because we are not sure about that.
Okay.
So, yeah.
All right.
Excuse me, Leticia.
Yes.
You had marked some cluster color coding for your clusters. Is
Yes.
that discrete or is that continuous?
No,
kind
it's
of?
discrete in the way we
And how many colors are you using?
Only 2 we were using. So we were using for those who are larger than the average mass and those which are smaller
No,
than the
there were
average.
some
Here.
multicolored pictures also.
For the ecstatic order, there it was continuous. For the ecstatic order, again before.
Yeah,
yeah.
these ones. That
Yes.
one. Yeah.
Yeah, this is continuous because it's an angle basically.
Oh.
Yeah. So yeah.
Did you try quorum sensing? Does it change? No.
Yeah, no, we didn't try. No, I don't know.
E potential. Right?
Yes.
So for example, if you take WCA, I mean,
Yeah.
your results
so
survive or?
what what will not survive for a softer potential is this part of the melting with the first order transition kind that I told you. So in the passive limit, these problems, which when they go to from the ecstatic to the liquid, we see first order phase transition. If we use softer potentials, this disappears. So this
I
little
see.
region disappears. But apart from that, there is no much difference. I mean,
Okay, no, I mean, if you take say truly hard spheres,
yeah, they are very hard hours. Huh? We use,
no, but still it is
Yeah.
not hard in that sense. I mean, like collision, I mean,
Yeah.
interchange, I mean, under collision, you interchange velocities. I mean, truly hard, I mean, infinite potential. I mean, you see.
I don't know, because then for the numerics, it appears to
Right.
be complicated because of the discontinuity.
No, there are some algorithms, right? I mean,
I know.
I mean,
I would-
collisions, simple collisions.
I would think that the same applies because ours is so,
Right.
so hard.
Yeah,
that, you
quite
know,
sharp.
yeah, yeah.
Second one is that you reported that Z greater than 2. So in the continuous transition, that would, I mean, at the critical point, so that would correspond to critical slowing down, like the bulk diffusivity goes to 0. I mean, do you draw some similar conclusions?
No, this is the Z of the phase separation. So the Z of, for example, Kawasaki dynamics for easing models, or model B dynamics in passive systems. All these phase separating systems have a Z equals to 3, and this is below the transition. If you think in terms of, you know, a transition point at critical temperature, for example, for the spin problem, it's not at the critical point; it's below.
Right,
It's-
but
it's when the system wants to order.
so this is not the dynamical exponent, or
Yes, it is. It is, but in the ordering phase, it's the
I see.
coarsening exponent.
Okay.
It's what is coarsening, or
Okay, right.
yeah, domain growth exponent. But
Thanks.
for problems, we conserved all the parameters.
How does the growth law depend on the Peclet number?
So it doesn't depend much. No,
No?
it's here it is, for example. So you see they have Peclet values. What will depend on Peclet is when you enter the critical, I mean, sorry, when you enter the scaling regime, and if you approach the end of this lobe, you have this MIP phase here, right? And this is Peclet. So if you move towards this boundary here, all this should disappear. So, but okay, it's difficult to control what's going on, you know, if you want to go to this critical point or to this, you know, limiting lines over there. But so the lowest value we are using here is 75, while here, for these parameters we have, this is roughly 50. So 75, we are somewhere here. If you get too close there, you have too many fluctuations, it becomes a bit of a mess.
No comments, questions? Okay, so if not, let's thank Leticia.
Thank you very much.
Nice talk. So we take a break and we come back at 4:30.